Hello again. In this lesson, we will look at how more current techniques rely on fully convolutional networks for semantic segmentation. The term fully convolutional indicates that the network is composed entirely of convolutional layers without any fully connected layers that traditionally might be found at the end of the network. Instead, the fully connected layers are replaced with convolutional layers. To semantically segment an image, a fully convolutional net takes in an input image and a set of labels which are image masks, one per class, of the same width and height dimension as the input image. It passes all of this input data through the network and produces a correspondingly sized set of output masks, or spatial output maps, which represent the probability of each pixel in the image being in each of the various classes. Let's look at this architecture in more detail. Supervised deep learning approaches using CNNs have been immensely successful in many high-level computer vision tasks, such as image recognition and object detection. What about exploring the use of CNN systems for pixel-level labeling problems? The intuition for why to do this might be the opportunity to learn a strong feature representation end-to-end for the labeling task, instead of handcrafted features with heuristic parameter tuning. However, there are significant challenges in adopting CNNs designed for high-level computer vision tasks to pixel-level labeling tasks. Firstly, traditional CNNs have had fully connected layers for class prediction at the end. Secondly, CNNs have convolutional filters with large receptive fields and produce coarse outputs when restructured to produce pixel-level labels. Thirdly, max pooling layers in CNNs further reduce the chance of getting a fine segmentation output by losing accurate spatial information, the where information. Pooling is great for classification and detection because it increases the field of view, but it's not so great for segmentation. It can result in non-sharp boundaries and blob-like shapes in semantic segmentation tasks. Fourthly, CNNs lack smoothness constraints that encourage label agreement between similar pixels and spatial and appearance consistency of the labeling output. Lack of such smoothing constraints can result in poor object delineation and small spurious regions in the segmentation output. Let's look at each of these challenges one by one. Firstly, the fact that traditional CNNs had fully connected layers for class prediction at the end. Fully connected layers limit the input size that the CNN can process. Our CNNs were restricted to operating on image patches of fixed size. The Fully Convolutional Networks paper from a team at UC Berkeley in 2015 popularized CNNs for dense pixel predictions without any fully connected layers. This allows segmentation maps to be easily generated for input images of any size. The second challenge were convolutional filters that have large receptive fields but produce coarse outputs. Let's take a look at the UNIT architecture from 2015. UNIT is based on an encoder with pooling layers, followed by a decoder. And there are shortcut connections between the peer layers of the encoder and the decoder. The encoder reduces spatial dimensionality with its pooling layers, and these shortcut connections to the decoder allow recovery of object details and spatial dimensions. Our third challenge is that max pooling layers in CNNs further reduce the chance of getting fine segmentation output by losing our where information. In this case, let's take a look at SegNet, also from 2015. SegNet is another fully convolutional network without any fully connected layers. It has more shortcut connections than UNIT, but instead of copying decoder features across from an encoder to a decoder, indices from max pooling decisions are cached and copied instead. That is, when the encoder max pooling layer makes a decision about the max value, it records the position of that cell such that it can reconstruct a sparse version of that cell in the decoder. The encoder remembers indices from its max pool selections and the decoder uses these pooling indices to perform nonlinear upsampling. This eliminates the need to learn upsampling. The upsampled maps are sparse. That is, they contain the max pooled value in the correct position and zeros elsewhere. And so, Segnet performs convolution to densify the feature map. These dense feature maps are next fed to a softmax classifier for pixel-wise classification. Finally, dilated or atrius convolutions do away with pooling entirely. These are convolutions where the stride across the input is dilated, giving the output a larger field of view, but without changing the dimensions of the image. The DeepLab version 2 algorithm uses atrius convolutions. Our fourth challenge is that CNNs lack smoothness constraints that encourage label agreement between similar pixels. Here, we can take a look at CRFs. The key idea of CRF inference for semantic labeling is to formulate the label assignment problem as a probabilistic inference incorporating assumptions such as label agreement between similar pixels. That is, taking the context surrounding a pixel into consideration. CRF inference is able to refine weak and coarse pixel-level label predictions to produce sharp boundaries and finely grained segmentations. As a result, CRFs can be used to overcome some of the coarse problems with using CNNs for our pixel-level labeling tasks. One way to utilize CRFs to improve semantic labeling results by a CNN is to apply CRF as a post-processing step, disconnected from the training of the CNN. In this setup, the deep network is unaware of the presence of the CRF during a training phase. The conditional random fields as recurrent neural networks architecture combines CNNs and CRF-based graphical models in a single unified framework. The CRF recurrent neural network, CRF-RNN, can refine coarse outputs from our convolutional neural network, CNN, in the forward pass, while passing error differentials back to the CNN during training. This way, the entire deep network can be trained end-to-end using the usual backpropagation algorithm. In this image, we can see the performance of the CRFs as RNN's approach on the Pascal VOC 2012 dataset. In the first column, we can see a fully convolutional CNN model only. DeepLab version 2 is next as a CNN plus a separate CRF. Finally, the fourth column is our CRF-RNN combined approach, where we train both end-to-end in the one deep network. And the final and fifth column is the ground truth, the actual correct labeling. In addition to using CRFs to solve our smoothness constraints problem, DeepLab version 3 revisits the concept of atrius convolution to better handle segmenting objects of different sizes. Modules using atrius convolution in cascade or in parallel were added to capture multi-scale context. The atrius spatial pyramid pooling module in DeepLab version 2 was augmented with image-level features encoding global context. DeepLab version 3 significantly improved performance over DeepLab version 2 without the need for an external dense connected CRF stage. So this has been a brief look at the evolution of semantic segmentation architectures. And the state of the art has certainly moved on since these particular network architectures. Perhaps the trend here is being reinforced for you. The trend for end-to-end trainable solutions. We started with handcrafted features. Our superpixels, SIFT, HOG, and deformable parts solutions were replaced by convolutional neural network feature extractors. Our human-designed object proposal methods were replaced by region proposal networks. And our smoothness constraints had external CRF blocks replaced with recurrent neural networks, the CRF-RNN approach, or with enhanced atrius spatial pyramid pooling schemes. Hi, in the next lesson, we will give an overview of our Jupyter Notebooks lab exercise on a small semantic segmentation problem. that of labeling airplanes in images. Having covered fully convolutional approaches to semantic segmentation, what about object instance segmentation? Instead of labeling all the dogs in an image with a mask, could we also identify individual dogs? Where were they? Could we count them? In the lesson following our lab, we'll look at some techniques for extending semantic segmentation to solve just such problems.